Okay, the numerical says a beam having T-shaped cross section with flange 200 mm by 50 mm and web 50 mm by 200 mm and I is equal to 1.134 into 10 raised to 8 mm raised to 4 is subjected to a vertical shear force of 100 kilonewton. Calculate shear stress at bottom and top layer, neutral axis, junction layer of web and flange, junction layer of flange and web. Actually, these two are same. There is only one junction there. There are no two junctions. So I don't know why they have put it like this. Also draw shear stress distribution diagram showing stress at above stated layers. Okay. So what we will do is first we will try to draw a diagram for the cross section of the beam. Like he has said, it is a T section. So T section is like this. Yeah, just like this, and it is symmetric about the vertical axis. So about the y-axis, I'll just show this as axis. So it is symmetric about the y-axis, and about x-axis it is not symmetric, right? It is asymmetric. So you have to find the location of neutral axis in this case. Now he has given this dimension right, then he is given this. Let me just write down those. This is 200, again 200, 150, and 50. And also there is y star. I'll just place these things now. So this length is 200. This is also 200. This is 50. And I missed this one. This length is also 50. Okay. Now I'm assuming the location of center of gravity somewhere here. It will not be exactly at the center. It will be slightly above this center of this. So this is my neutral axis. I will show this as N A. Right? Now, what are the points he has asked? Bottom and top layers. That is, this is top layer. This is bottom layer. Neutral axis. That is this portion. And junction layer of web and flange and web. It is this layer only, right? This point. So yeah, basically what he's saying is junction layer of web and flange is this point, and flange and web is this point. Basically, these 2 points he is asking. So I'll just name them. This is A, this is B, this point is C, this neutral axis, call it D, and the bottom fiber, I call it E, right? So these are the points at which I have to find the shear stress. Now I'm showing this location of center of gravity or the neutral axis from the bottom fiber. Let us say here. This is y star, and this will be y. Okay, so this is our diagram. Now with this, let us start calculating the shear stress. So first thing I have to do is find the location of center of gravity or the neutral axis. So solution, location of NA, neutral axis, right? So that is your y star is equal to what is the formula? Sigma a1 sigma a y divided by sigma a, right? So I have only two rectangles, a1 y1 plus a2 y2 by a1 plus a2, right? This is one rectangle and this is another rectangle. So I'm starting from here with respect to this surface. I'm finding this y star. So if you consider this rectangle, the area will be 50 into 200 into y 1 is again 200 by 2. Please mute your mobiles. Okay. The second rectangle I have is 200 by 50. So it is 200 into 50. Put that in a bracket. Now the location of the center of gravity of this rectangle is at 25 mm above point B, and B is at 200 mm from E. So 200 plus 25, it is 225. So into 225 divided by, see both the areas are same, 200 by 50, 200 by 50. So I'll write it into 200 into 50. Okay, that is my area. Now for calculation it's very simple. You see 200 by into 50 is there in all the three places, 200 by 50, 200 by 50, 200 by 50, right? So you can just cancel that. So it will be 100 plus 225 divided by 2. So let's do that. 100 plus 225, 325 by 2, 162.5 is equal to 162.5 mm. So that is the location of y star, right? this is 160. Two point five. Now this total length is 200 plus 50, 250. 250 minus y star will be this, I'll call it as y1, right? And y1 will be equal to 250 minus 162.5, 87.5. You need this for calculation later. So y1 is equal to 250 minus 162.5 equal to 87.5 mm. Okay, so I got y star and y1 now. Now I can find the shear stress at all the points. Okay, let us start. Uh, Shear stress at point A, right? So which is upper layer, or what layer said is top layer, right? So at top layer of section A y bar A into y bar is equal to 0, because above this, say top layer is this, you have to consider the area above that layer. Now above this layer there is nothing, right? So a y bar will become 0. Therefore shear stress here is 0. Actually I will do one more thing here. uh, Point A and point E, right? So top, bottom layer. At both these places, the shear stress will be 0. So I have determined these 2 points. Next, I have to go to point B, which is junction of the flange and the web, or the bottom layer of the flange, right? So I'll just copy this at point B. Now shear stress at any point is given by where is our formula? This one. So we have tau is equal to F by I into A y bar by B, right? So I'll put this here. We have tau is equal to F by I into A y bar by B, right? Now at point B, A y bar is equal to what? See, this is B. Area above the B is this rectangle, correct? And this rectangle area is 200 by 50. So I'll just put that 200 into 50 into y bar. Y bar is what? The location of the center of gravity of this rectangle from the neutral axis. So the center of gravity is at a distance of 50 by 2, that is 25 mm from B, and from neutral axis it is y1 minus 25, right? So into y1, I'll write it for the first one, minus 25. So this is equal to 200 into 50 into y1 is 87.5 minus 25, and that value is 87.5 minus 25 is this into 50 into 200, right? So copy this here. So it is 625000. This is the AY bar at uh, point B. And at B, what is the width? Width of the section at B is 200. So B, and B is equal to 200 mm. Right? Now let us use this equation for shear stress. So shear stress is given by F by I. Now what is F here? F is 100 kilonewton. So you have to put it in Newton. 100 kilonewton means into 1000. So 100,000 divided by the value of I is 1.134 into 10 raised to 8, right? So 100,000 by I is this value. A y bar, you can just put this value. So A y bar is this, divided by B is 200. So let us calculate this. 100,000 into 625,000 by 200 by 1.134 by 8 10 raised to. So it is 2.755 or 2.76 megapascal. Okay, so I have found the shear stress at point B. Next, I have to find the shear stress at point C. See, B and C are at same location. With respect to NA, the distance is same. So the area above the section will remain same, but the width is different. At B, the width is 200. At C, the width is only 50 mm, right? So shear stress at point C. So I can write here A y bar. I'll directly write the value 65,000 because it is not going to change, and B is equal to 50 mm, right? So I have these. Now here if you see, what you can do is this value I got by dividing this, because rest all things remain same. AY bar is same and this term is not changing. So 625000 divided by 200, when you did this, we got 2.76. So you multiply 2.76 by 200 and divide by 50, you will get the shear stress at this point, right? So that is short way of doing calculation. If you want, you can do it the same way. 2.76 into 200 by 50. So that will be 11.04. So I'll just copy the same expression. This will be 50 and this answer is 11.04 megapascal, right? So I got the shear stress at point C. Now I have to find at D. So if I do that, then my numerical is over. I just have to draw the distribution curve, right? So at D, it is neutral axis. So just write that shear stress at point D within bracket neutral axis. Okay, now A Y bar. Let us go back to the diagram. See, this is my section now, right? And A itself is my section. Y is equal to 0. So now, with respect to this, what is the area that is available? It is this entire rectangle, 200 by 50, plus part of this web, right? From C to D, and width equal to 50 mm. This rectangle, right? So you have to use this area into y bar of this plus this area into y bar of this. So let me do that. So the top rectangle is 200 by 50 into this distance, 87.5 minus 25. I will calculate it and put, otherwise the equation will become very long. 87.5 minus 25 is 62.5. 62.5 plus the length CD is actually 87.5 minus 50, right? From here to here it is 87.5. You subtract 50 from this, you get this height. So that is 37.5. So the area will be 37.5. Actually it is 50 into 37.5 into 37.5 by 2. Okay, now let us calculate this. 200 into 50 into 62.5 plus 50 into 37.5 into 37.5 by 2. So just copy that. So this is my AY bar at point D, which is my neutral axis, and B is equal to 50 mm here. At neutral axis, width is 50 mm. Okay. So use this equation again. AY bar value is this, rest all remains the same, right? So let us calculate this. 100,000 into 660,156.25 by 50 by 1.134 by 8 10 raised to. So it is 11.64 megapascal. 11.64 megapascal. So this is the maximum shear stress at the neutral axis. And the last point is E only, which we have already calculated. Now I have shear stress at all the points, so I can draw the shear stress distribution curve. So for this, let me use a different color which I have not used. Use purple now. What you have to do is first draw a reference line, vertical line, and then you project all the points onto this line. So at neutral axis I'll have maximum. At this point it will change, and at this point it is 0, right? So let us go back to the solution. What is the shear stress at B? It is 2.76. So let us say 2.76. Let us say this is 2.76. Okay, because at that point you will have two shear stress, and at C it has suddenly increased to 11.64. So this is 11.64. Sorry, this is D. C is 11.0. Okay, not much of a difference, right? And at D it is 11.64 somewhere here, and at E it is 0, right? So it should be a curve like this. So first I will draw a straight line here, right? At the junction C and B, there is a sudden raise in the shear stress, and here it will be a parabolic curve, and from here to here it is parabolic curve. So let us show this as a parabolic curve. Just have to show it as a curve like this, and then from here to here, right? So this is the shear stress distribution for this particular cross section, right? You have to just write the values, shear stress value, whatever you have, you just have to write at these.